Hello everyone, so today we'll be discussing graphing functions using derivatives. So up till before derivatives, at least, we haven't been able to graph functions with as much specificity as with derivatives. So now we can, in addition to maximum and minimums, we can also graph points of inflection. So points of inflection are just where concavity of a graph changes, and concavity refers to whether it's concave up or concave down. It's easily I guess defined visually. You can see this graph right here is concave up, this graph right here is concave down, simple parabolas, whether they open up or open down pretty much. So here I've listed out the steps to graphing using derivatives. So first, always given a function f, you find the first derivative, you set that equal to 0, then you solve for x. So these values, after solving for x using the first derivative, will be your critical values for maximum and minima of the function. So so then after you find a maximum or minimum value, if there are any, you find the second derivative, set the second derivative equal to 0, and once again solve for x, and these are again your critical values. These critical values, however, tell you if there are any points of inflection, which, like I said before, refer to concavity of the graph. So you can pause the video and look at these steps or write them down if you need. Our first example function will be f of x equal to x to the fourth minus 4x cubed. Simple polynomial function. So, like I wrote in the steps, the first derivative that we want to take, it's simply use the power rule, so you get 4x cubed minus 12x squared. Set that equal to 0, and you're left with 4x squared. Factor that out, x minus 3, and that gives you x equal to 0 and x equal 3. These are critical values. So what we do with these critical values is do what we call the first derivative test. So start by making a number line and place your critical values on the number line, and we, in the intervals given on the number line, so any value less than 0 from 0 to 3 and then greater than 3, we find if the derivative 4x cubed minus 12x squared is going to be positive or negative. And this will tell us if the function is increasing or decreasing, because remember, the first derivative is just the slope of our original function. So when it's less than 0, the first derivative is less than 0. 0 to 3, it's negative, and then greater than 3, it's positive. So it didn't change from before 0 to after 0, so there's no maximum or minimum there. But the slope went from negative to positive at 3. So this will be a local minimum value. It'll be a local minimum. So we have one local min, and now we proceed with the problem. Find the second derivative of the function, and once again, that's a simple power rule. 12x squared minus 24x, and set that equal to 0, factor out 12x, and we're left with x equals 0, x equals 2. So these are again critical values for points of inflection. So we do the second derivative test here, which is exactly the same process as the first derivative test. Place your critical values on the number line and test if it's positive or negative in each of the given intervals. So when it's less than 0, it's going to be positive. When it's between 0 and 2, the second derivative is going to be negative, and then positive when it's greater than 2. So we can see that the second derivative changed signs from before to after 0, and from before 2 to after 2. So there's a point of inflection at x equals 0 and a point of inflection at x equals 2. So we want to substitute all these x values 3, 0, and 2 into our original function to find the y values for each of these. So f of 3 equals 3 to the 4th minus 4 times 3 cubed. So that's going to be 81 minus 27 times 4 minus 108, and that gives us negative 27. So that's, and then I'll just write it out, local minimum of negative 27 at x equals 3. And then our second one, our first point of inflection is at x equals 0. So f of 0 is 0. So POI, point of inflection at, of 0 at x equals 0. And our second point of inflection is 2. F of 2 is 2 to the 4th, which is 16. Minus 4 times 2 cubed, which is 32, so which is negative 16. So there's a point of inflection of negative 16 at x equals 2. Okay, so we have all of our values here, and so we use these values to graph. So write this down if you need to. I'm going to sketch a graph of it on another page. Okay, so we had our local min of x equals 3 and y equals negative 27, so that's about right there. This is just a sketch, so don't worry too much about being exact. Point of inflection 0, 0 right there, and we have another point of inflection 2, negative 16, just about there. Okay, so from our previous sheet we can tell that the okay, what am I looking at? Excuse me. Okay, so we're looking at 0, 0 here, which is the leftmost point. So the concavity was positive before 0 and negative after 0. So a positive concavity opens up and a negative concavity opens down. So that's our first little part of the graph there, and I'll just put an arrow. And at 2, negative 16, we had another point of inflection. It was negative concavity, which I already drew in before 2, and then a positive concavity after 2. So it'll be opening upwards after this. And then to finish off the graph, we see that after 3, the slope is positive. So we'll draw it opening, 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 and then it's going up because, like I said, the slope of the function is positive after 3. So there it is. That's a rough sketch of I'll just write down the function one more time. There it is. We'll do a trig function this time. F of x equals x minus cosine x. First derivative, it's just simply plus sine x, because the derivative of cosine x is negative sine x, and then 2 negatives is a positive. So 0 equals 1 plus sine x. Sine x is negative 1, and then we have, I'll give it an interval on 0 to 2 pi. Okay, so that's 3 pi over 2, and just like last time, do our first derivative test, and we just include the endpoints of our interval if they are given. So 3 pi over 2 is going to be about right there, and we can see that if you substitute a value between this, the function is going to be positive in between 0 and 3 pi over 2, and it's also going to be positive from 3 pi over 2 to 2 pi. So the first derivative's increasing, so the function is increasing throughout, so there are no maximum or minimum values on this interval. There are no relative maximum or minimum. 0 and 2 pi are the endpoints, so they may be maximum, minimum values there. f2 prime of x, so we're doing our second derivative now. It's just cosine x, and set it equal to 0, and we have x values of pi over 2 and x equals 3 pi over 2. Once again, same process, so 0, 2 pi, and then put in our critical values of pi over 2, 3 pi over 2, and then figure out if it's positive on these on the 3 given intervals we have here. So it's going to be cosine is positive here, negative between pi over 2 and 3 pi over 2, and then positive on that last interval. So it goes from positive to negative at pi over 2. That's a point of inflection. So positive as in concave up to concave down at pi over 2. Then it goes from concave down to concave up at 3 pi over 2. So that's another change in inflection. So that's a point of inflection. Endpoints. We want to put our endpoints into the function. F of 0 is going to be -1, and okay, and then f of 2 pi is going to be 2 pi minus 1. So these are absolute maxes and mins because they're the endpoints and there was no relative maximums or minimums in between, so we know for sure that these are absolute maximums and minimums on the given interval. So we can say, I'll just abbreviate, absolute minimum is -1 at x equals 0, and then absolute max is 2 pi minus 1 at x equals 2 pi. And then now we can look at our points of inflection. So f of pi over 2 is pi over 2, and f of 3 pi over 2 equals 3 pi over 2. So that's a point of inflection at point of inflection is pi over 2 at x equals pi over 2, and point of inflection is 3 pi over 2 at x equals 3 pi over 2. So now use this information just like the previous example to draw out the graph. We have to get 2 pi. Okay. So our absolute minimum 0, -1, and absolute maximum 2 pi minus 1. That's about right. And points of inflection at pi over 2 and pi over 2 and 3 pi over 2, comma 3 pi over 2. So looking back at our sign charts for the second derivative test, from 0 to pi over 2 it was a positive concavity, and it was a negative from pi over 2 to 3 pi over 2. So we'll depict that in the graph. So positive concavity, so I want it to be opening up till our point here, and then opening down. Not the best sketch in the world. And then from 3 pi over 2 to 2 pi, it's positive concavity. So once again, it's opening up there. So there's no maximums or there's no relative maxima or minima in between the endpoints, as we can see from this. And we have 2 inflection points, pi over 2 and 3 pi over 2. We'll do one last example, so it's going to be a little harder, but I'll write it out, and you guys should pause the video if you can and do that on your own and check back after you're finished. Okay, so I'm assuming you've done the problem. Okay, so we have our minimum, our maximum, and 1 point of inflection. So once again, we'll just use this for the graph. And I guess I forgot to mention, since this is a really easy zero, this isn't the focus of this video, but that's a really easy zero to find right there. You know, x equals 5 halves. Minimum at 0, 0, maximum at 1, 3 halves, 1, 1.5 right there, and negative 1/2, 1.89, so about there. Okay. And then, like I said, we have a 0 at 2.5, so 2.5, so just about right there. So when we're looking at our previous sine charts, we can tell that we have point of inflection is at negative 1/2, 1.89, and it's concave up before negative 1/2 and concave down after. So I'll try to exaggerate it as much as I can in the space. Okay, so it's concave up before and concave down after. So then from there, it's concave down the rest of the way. So we reach our relative maximum there, come down to our 0 and follow through, and just put an arrow there. So that's the graph of that function. Thank you for listening. I hope you understand graphing using derivatives a little better now.